Hi guys, welcome to our channel of Sciences and Mathematics. I'm Ernest, and today we are going to look at the concept in wave particle duality. Of course, we have discussed some of the concepts that are maybe building up to the broader topic of quantum mechanics in some of our videos, and this includes the de Broglie's hypothesis, the Heisenberg's uncertainty principle, and some of the experiments that were done in order to back up this concept of quantum mechanics, like the photoelectric effect, the black body spectrum, and the Max Planck's quantum theory that we have already done some of our videos. I'm going to put the link of the videos in the description box. And then we talked about the concept of the X-ray that were done by the other Compton, and lastly about the Young's double slit experiment. So for today's discussion about the de Broglie's, the Schrödinger's wave equation, we're going to look at a version of the Schrödinger's equation, which is a Schrödinger's time-independent wave equation. And we're going to see that this one is very important, especially in trying to describe the quantum systems by trying to give their energy, momentum, and then maybe a possible location. Now, the Schrödinger's equation is very important, especially in the study of subatomic particles, and of course, the study of wave mechanics. So we're going to find the relevance as we discuss about this in the broader topics that entail the concept of physics and chemistry. And this is going to give us a basis in trying to solve problems that we may come across that relate to the same topic. So without further ado, thank you and welcome. So as I've said, today's topic of discussion is the concept of the Schrödinger's equation. And as I've said, the Schrödinger's equation is very important, especially in trying to understand the concept of quantum mechanics topics, some of which we have already discussed in our video that I'm going to put in the link in the description box, as I've said. And this is going to give us a basis for understanding the atomic structure that we learn both in chemistry and physics. Now, the Schrödinger's time-independent equation stems from the fact that, of course, there was a concept of a wave particle duality that was advanced by some of the scientists like the Niels Bohr and the Louis de Broglie and others, of course, who are trying to figure out how they can be able to find a relationship between matter and waves. And we have, of course, discussed in one of our videos about the concept of matter waves, which are very different and from the normal electromagnetic waves that we have seen. So in our discussion about the Schrödinger's time-independent wave equation, it's going to basically assist us to describe motion of a subatomic particle, which is an electron, when it's accelerated in a potential difference, of course, V. And from the Coulomb's laws of attraction, we can be able to illustrate this is so in this case, if we have just a minute, positively charged particle that is moving from this specific point, it will move in that direction according to the laws of attraction. So it's going to move in this specific direction, going that way. So if the particle was at this particular point and it was experiencing the forces of attraction, then therefore it will be possessing potential energy. And basically when it's in motion, then we can be able to describe its kinetic energy. So in this sense, we're going to see that the work it's going to do, it's going to be the maximum kinetic energy. And from the energy, from the change in kinetic, the energy work theorem, we know that the change in potential energy is going to give us the kinetic energy. Now this is a concept upon which we are going to see that an electron that is moving in a potential difference can be described in terms of momentum. It can also be described in terms of its energy, and basically the Schrödinger's equation is going to give us a way in which we can be able to describe its position. Now from the de Broglie's equation, we talked about the concept of de Broglie's wavelength, which we have given as Planck's constant over the momentum. So basically this is a constant which is a Planck's constant, and we're going to, it's just a constant which is given negative 34 joule seconds. So this a constant is basically given, it does not need anyone to confirm it or just to remember it. We're given that constant, and this is momentum which is a product of mass times velocity from classical physics. So we can make the, or maybe just have a manipulation of this specific equation by making P the subject of the formula, which is going to be given as h over lambda, where lambda implies wavelength. Now, having said that, we know that from classical mechanics we can be able to describe kinetic energy as half the product of mass times the square of velocity, which is half mv squared. Now we can be able to work around and manipulate this kind of an equation to have a different version. Now suppose I have a number a over b, and then I multiply both sides by 2. I'm not going to change the value of that specific number. Basically it's going to remain the same because that scalar multiplication does not change it. So if I have this specific equation and then I multiply both sides by mass, so this basically can be represented in form of mv squared over 2. So basically if I multiply both sides by mass over mass times 2. So I've multiplied both sides by mass, both the numerator and the denominator. I'm going to have m squared v squared over 2m, which basically still represents kinetic energy in that specific order. I've just multiplied by 2, so it does not change its value. Therefore, I can have kinetic energy represented as m squared v squared all over 2m. And we have said that the product of mass times velocity gives us momentum. Therefore, this version of an equation can be written as momentum squared over 2m. Now, from this specific case, we are going to see that we can be able to have a version of this kinetic energy in terms of h over lambda by doing a substitution for that part of momentum. Now, having said that, we can say that momentum squared over 2m can be given as momentum squared times 1 over 2m, which is equivalent to h from this equation, h over lambda times 1 over 2m. But remember, this one was momentum squared. So therefore, working for that equation, we can have still this is kinetic energy, which is this one, or this one, or this one, represented as the last bit of this equation, which is h squared over 2m lambda squared. So this is going to form part 1 of our equation. So in case of maybe space, a limitation of space, remember that we have just reached at that point in trying to figure out how we can describe kinetic energy in a different way. Now suppose we have a wave function that is represented by this specific symbol, which is psi. So if we have a wave function that is represented as psi, which is a function of the distance and time, we're going to see that this wave function can be represented in terms of a trigonometric function as psi is equals s a, the sine of 2 pi all over lambda. Yeah, just because of space, I have to write a small one so that we can be able to utilize. So psi can be given as rho psi with respect to RT, which is distance and time can be given as psi, which is a 2 pi, or this the sine of 2 pi over lambda, whereby this lambda for a wave. Now this is a wave function that is given as that. Now for a wave, as we talked about the concept of wave particle duality, this this wavelength represents the wavelength of a wave as per the de Broglie's representation. So therefore, if we have a wave function that is represented using this one or this one, this particular section, which is A, represents amplitude of that specific wave. So we can have this one as an equation that is representing a wave. Now if we differentiate this particular equation with respect to that function x, we're going to differentiate it twice so that it gives us a specific probability. So the first differential of psi is going to be given as the first differential of psi with respect to x is going to give us a. So the differential for this specific trigonometric function, we have looked at the rules of differentiating trigonometric function. For now, for the sine, it's going to be the cosine, and therefore we're going to have 2 pi over lambda as a constant, which is brought on this side, and then we are going to have the cosine over this specific value that we have for sine. So the second differential is going to give us this psi, this squared psi dx squared gives us a. Now again we bring that one, so it is 2 pi over lambda squared, and this is going to be the sine. The differential of this, the cosine, is going to be the sine 2 pi over lambda. So therefore this is going to form our equation 2. Now that we have had our equation 1 for representation of kinetic energy in this specific format, now that is going to form our equation 1. Now trying to figure out how we can be able to do a substitution of our equation 1 in 2, we can be able to just do a simplification for this and have this one given as a 4 pi squared over lambda squared, the sine of 2 pi over lambda. Now we can be able to do a rearrangement for this specific equation, and we come up with a form of this second differential given as a, the sine of 2 pi over lambda, and then times, I'm just expanding it for the sake of understanding, so we are going to have a 4 pi squared over lambda squared. So this is just a version of the differential, so this one implies that one. It's a second version of the differential of that. But from this equation, we have seen that we can be able to make, or maybe just have a definition for the inverse of lambda squared, which is a section of the part of this. So remember, this one can be written as h squared over 2m times 1 over lambda squared. So this fraction of the reciprocal for lambda squared can be represented using a different version. Now I'm just going to derive it from this specific equation, which is a second differential. So I'm going to do away with this section here. So that we can have so remember, from our equation there we had kinetic energy given as h squared over 2m lambda squared. Now we need to find a way of representing this reciprocal from this by just doing a multiplication and finding out. But remember, from our illustration for this specific psi, there's a portion of this equation that is representing psi, which combines this one and this amplitude. So this one represents the definition for that wave function, whereas from the representation of kinetic energy, we can be able to find the reciprocal of that. So therefore, 1 over lambda squared can be found by dividing this section by 4 pi squared, and then remembering that the combination of this amplitude and this section of the trigonometric functions gives us psi. So therefore, this is going to be 1 over 4 pi squared psi times this part of the second differential, sorry for that, dx squared. So just like that. So I've just written this one here for illustration. So it's going to give that portion, and this is going to form our equation 3. So this is our equation 1, this forms our equation 2, and this forms our equation 3. So we have arrived at this by just doing a substitution of this and taking this to the other side to remain with only the reciprocal of that. Now we have seen from this specific equation that we can get the reciprocal of lambda squared. So we'll take this specific part of the equation and substitute it in that form, the reciprocal of lambda squared. Therefore, we'll have the kinetic energy represented as h squared over 2m times 1 over lambda squared. So I'm going to do this portion of the substitution for this specific equation, and therefore arrive at an equation which is represented as 1 over 4 pi squared d squared psi over dx squared. So that forms a way in which we can be able to represent kinetic energy using that specific function. But we have a reduced form of Planck's constant that I'm going to use in this case. Of course, it is written as h bar. Let me use this one. So this reduced form of Planck's constant is written as h bar, which is h, the normal h over 2 pi. So therefore, if I try to square this one, I'm going to have h squared 4 pi squared. Now, looking at this portion of the equation, we can be able to see that this specific form of reduced pi has been squared in that equation. So therefore, I can write that equation in a different format by trying to infuse that concept of h bar squared. So therefore, this section of my equation for kinetic energy is going to be represented as, so I'm just going to do away with this one because of space. So that section of my equation can be represented as h over 2m psi, the second differential of psi, after I've done this substitution for h squared. So this basically represents kinetic energy, and we know that kinetic energy is a negative work of that potential energy that we had mentioned, change in potential energy that we had mentioned. Now from the equation of energy of a system, we know that the total energy of a system can be given as the sum of kinetic energy. This is the sum of kinetic energy plus potential energy. Therefore, we have already defined the concept of kinetic energy. We can make kinetic energy the subject of the formula and find that kinetic energy can be represented as the total energy minus potential energy. Now, in this case, we're going to represent this specific form of the equation by energy as E minus the potential energy, let's give it V. Now, this is going to form part of equation 4 for general representation of this kinetic energy. Now in this case, if we try to do this equation for kinetic energy from what we have already defined it here, then we can be able to give it this specific equation as change in energy, total energy minus potential, is equals kinetic energy, which is negative h squared over 2m psi, this part of the second differential of psi, which is a wave function, dx squared. So therefore we can have this version of the equation from the relationship of potential and kinetic energy from the total energy of our system equation that we have given. Now still we can do a rearrangement for this specific equation to have this function of a second derivative, which is going to give us, so therefore we are just going to have a representation for d squared dx squared from this by just doing a division and multiplication of this specific sign to give us negative 2m all over h r squared into that change in energy that is representing kinetic energy, and we are going to have this one multiplied by psi. So still in this case we can be able to rewrite this equation and have it as the second differential with respect to x plus, so we just do a calculation for that. We're going to have this portion of the equation taken on this other side plus 2m all over h squared into p minus minus v psi is equals 0. So we have taken the whole part of this equation on the other side, just trying to rewrite that form of an equation to have this specific format of the equation. Now this last bit of the equation is what forms the Schrödinger's wave equation, that is explaining the motion of an electron in a potential difference v. So therefore this Schrödinger's time-independent wave equation that is used to represent the motion of an electron in a potential difference v. So therefore, as we can see, we have encompassed the concept of energy, and we are going to see that using the wavelength for that particular wave equation that we have talked about, the de Broglie's wavelength, then it's going to behave as a wave. Therefore, as we said, the concept of this Schrödinger's wave equation assists us to try and explain all the possible information that is contained in a quantum system. And of course, we are going to see another version, as we have said that this is a time-independent equation. We're going to see another version of this Schrödinger's equation in a different video, but for this case, this is how we can be able to define it, and it will assist us to determine the location and energy and momentum of a particle, and of course try to explain some of the concepts that we come across in wave mechanics. So I hope that as we have gone from step to step to trying to define this equation, it's going to find a wider application now. In any case, maybe we are trying to talk about the energy of a particle, or maybe some of the concepts in an atom, and we mentioned the concept of Schrödinger's equation. I hope that this video is going to assist us in trying to interpret the information that we are mentioning in those specific aspects. So for that case, this is it for today, guys. I hope that we are continuing to subscribe to our channel so that we can be able to find a larger base for us to discuss some of the concepts and assist one another in trying to achieve our main objective, of course, in trying to look at society from the scientific lens and try to find solutions so that we can be able to solve challenges that we come across in our societies. So that is it for today, guys. Bye. God bless.